All right, I think we can go and get started. So just a reminder of where we left things in the previous lecture. So we started our discussion of motion planning. And specifically, we started talking about motion planning in discrete spaces. So we thought about how we can take a continuous motion planning problem, so motion planning in a continuous space, discretize it, which then allows us to use some pretty powerful techniques from graph search algorithms. So specifically, we discussed two algorithms in the previous lecture, breadth first search, which is BFS, and depth first search, DFS. And I mentioned that there are basically two considerations when we're thinking about motion planning. And this is similar to the two considerations we had when we were thinking about feedback control. So when we thought about feedback control, we wanted our feedback controller to stabilize our system and to be optimal in some sense. Similarly with motion planning, we want feasibility. So we want our motion plan to find some path from a starting configuration A to a goal configuration B that doesn't collide with any obstacles. And this was achieved by BFS and DFS. The second thing we want is some kind of optimality. So we might have time or length of the path or some notion of energy that we want to minimize. So we didn't really talk about that in the previous lecture. The goal for today is to discuss algorithms, still graph search algorithms, still motion planning on discretized spaces that allow us to find optimal motion plans. So this was kind of the general structure of the algorithm we looked at in the previous lecture. So both breadth first search and depth first search had this general structure. The main data structure we were keeping track of was this queue, this priority queue denoted by the letter Q. We basically take things out of the queue, explore its neighbors, and then add things to the queue, take more things out, and so on. So incrementally searching through the graph until we get to the goal location. So we're going to still maintain this general kind of structure of the algorithm, but we're going to make two new modifications. So the first one is that we're going to implement this q.getVertex a little bit differently. And basically, we're going to have some prioritization that's different from BFS and DFS. So BFS and DFS use either first in, first out, or last in, first out. Today, we're going to implement this q.getVertex function a little bit more cleverly than we did in the previous lecture. So that's going to be one, the main really modification. The second modification is this part of the algorithm, so this resolve duplicate x prime. So I'll say more about that as we discuss the algorithm. Okay, so I guess let's first define exactly what we mean by optimality. So what are we trying to be optimal with respect to, and how do we define some notion of performance or metric? So the way we're going to define optimality is by thinking of a cost function, which is also known as a loss function. And the way this is going to work is that for our discretized problems, we have these nodes, these vertices and edges. So we have this graph structure. We're going to assign a cost or a loss. Those are terms that are used analogously. We're going to assign each edge a scalar value, which is we're going to think of as a cost or a loss. And the total cost of a plan is basically the summation of all the costs for each edge along the plan. So if we look at one particular path from A to B, so that's one particular plan, we can sum up the costs along all the edges, and that's our cost for the path. And our goal is basically to find some way of getting from the start configuration A to the goal configuration B without colliding with the obstacles that minimizes the total cost. So this is a fairly abstract formulation. So the cost could correspond to time. The cost could correspond to energy. The simplest one is just length. So if you just associate the number like 1, let's say, just 1 unit of distance to each cost, that's another perfectly reasonable cost function. But in principle, you could encode some complicated cost structures in this formulation. So as an example, if you think about maybe going up a hill, So things that are on this side of the graph have higher costs. So edges on this side have higher costs. Maybe edges on this side have a lower cost. Yeah, you can make up, I guess, many different cost functions. We're just going to work with this abstract formulation. Okay, so the algorithms that we're going to discuss today, it's going to be useful to keep track of 3 different kinds of vertices. So I'll give them some names. So the first kind of vertex that's going to be useful to keep track of are vertices that we're going to call unvisited. So these are basically vertices that we have not yet explored. So we haven't added them to our queue yet. The second kind of vertices are what are known as alive vertices. So these are vertices that are in the queue. So there are things that we haven't yet taken out of the queue, so we haven't explored the neighbors of the alive vertices. And finally, the third category of vertices are what we're going to call dead vertices. So intuitively, these are vertices that don't have anything further to contribute to the search. More formally, or more precisely, these are vertices whose neighbors we have explored. So essentially, these are vertices that we've taken out of the queue and then explored their neighbors. So yeah, this is just some terminology that's going to help us as we describe these optimal planning algorithms. Okay, so the first optimal planning algorithm that we're going to discuss is what's known as Dijkstra's algorithm. The main idea behind Dijkstra's algorithm, as I mentioned previously, is to modify how the q.getVertex function is implemented. So what do you prioritize for taking out of the queue and exploring? And Dijkstra's algorithm is going to use an estimated cost to get from some vertex, which we're going to call x. Get to a vertex from the starting vertex A. And that estimated cost is going to be what we use to prioritize which vertex to pull out of the queue to explore. So we'll get into the details of that. And I guess just as a reference, I mentioned the textbook Planning Algorithms by Steve Leval. It's a really excellent reference for all things motion planning. So these graph search algorithms, Dijkstra in particular, is chapter 2.2.2 in case you're interested in exploring more. Okay, so I guess here's the idea behind Dijkstra, a bit more carefully written out. So for each vertex x, we're going to define the scalar quantity c star of x. That's going to correspond to the optimal cost to come from A to x. So this is the optimal, so that's why we have a star there. What we're going to maintain is an estimate of C star. So an estimated optimal cost to come from A to x for each vertex x in our graph. And the priority queue will be sorted according to this estimate, which we're going to call C of x of the optimal cost to come from C star. So C star is the optimal, C of x is what the algorithm actually maintains. That's the estimated cost to come to a vertex to a vertex x from the starting vertex A. And as the algorithm proceeds, so as we explore more and more vertices, we're going to update these estimates, C of x, for every vertex x that we're exploring. So that's the general idea. We're basically modifying what we take out of the queue based on this estimated cost to come. Okay, so we're going to initialize C of x for all x other than the starting vertex to be just infinite. For the starting vertex, we know what the optimal cost to come is. It's just 0. So to get from A to A, there's no cost that you incur. There's no edge that you need to traverse. So we're just going to initialize C of A, which is the famous C star of A, to be 0. For all other vertices, we're going to say C of x is going to be infinite in our initialization. And then each time a vertex is considered, so each time we pull a vertex out of the queue, we're going to estimate, or we're going to update the estimated cost to come. So C of x prime is going to be updated to C of x plus the cost associated with the edge that gets from x to x prime. So if you remember the algorithm for BFS and DFS from the last lecture, we consider some vertex x that we pull out of the queue. We then look at its neighbors. And so for that step, when we look at the neighbors of x, so for each neighbor x prime, we're going to do this update. So we're going to take the estimated cost to come for the vertex x, and then we're going to add in the cost of traversing the edge that takes you from x to x prime. Okay, and then the line, which I mentioned at the beginning of the lecture, this resolve duplicate x of the algorithm, is basically going to account for the fact that there might be multiple ways to get to some vertex x prime. So there might be one way we got to the vertex x prime previously in the algorithm. Maybe we, while exploring the graph a bit more, we found a different way to get to x prime. We're going to update the estimated cost to come for x prime if the newly found path is better than the one we found before. So if the new, like C of x plus L of E, is lower than the previous kind of best estimate of the cost to come for x prime, then we're going to update that estimated cost to come. And then we're going to just reorder Q accordingly based on the new estimated cost to come. Okay, so I guess I'll go through an example, so hopefully this will become super clear when we go through a concrete example. Here I'm just trying to convey the intuition and some of the data structures and the basic structure of the algorithm. I guess one question you could ask is, we're really maintaining an estimate C of x of C star, so estimated cost to come. But when does C of x become actually exactly equal to the optimal cost to come for a given vertex x? And it turns out you can prove via an induction-based argument that once x is dead, so basically once you take out x from the queue and explore its neighbors, the estimate C of x for that dead vertex x becomes equal to the optimal cost to come C star of x for that vertex x. So yeah, basically when the vertex becomes dead, we know that x cannot be reached with a lower cost. So this I think it's not completely obvious, but it's something that you can prove via induction. And if you want to see the proof, that's laid out in chapter 2.2.2 and 2.3.3 in the planning algorithms book. Okay, so I guess any questions on the general structure of the algorithm before we go through a concrete example? All right, so this is the example graph that we're going to look at. So it has these vertices. Again, the goal is to get from the starting vertex A to the goal vertex B. And I've assigned some costs to each of the edges. So the numbers that are kind of labeled along each edge correspond to the cost of traversing that edge. So if you want to get from A to V3 or V3 to A, you assign or you incur a cost of 2. If you want to get from V2 to V1 or V1 to V2, you get a cost of 3. And I guess I'll mention again, as I did in the previous lecture, right now we're looking at undirected graphs. So the cost of going from some vertex V1 to V2 is the same as going from V2 to V1. So all of these algorithms you can modify in a not kind of too complicated way to also handle graphs that are directed. So you might have some cost of going from V1 to V2, but a different cost of going to V2 to V1. I think it's simpler, though, to work with the undirected graphs version. Okay, so this is the setup. So let's go through Dijkstra's algorithm and see it in action. Questions?
Yeah, sorry. Does the user like set the cost?
Yes. Yeah, so you can think of the cost as like part of the problem definition. And the cost is going to depend on the specific application that you have in mind. And we'll discuss a little bit about how to, or like some of the challenges with defining costs. But yeah, for now, just imagine that someone, like a user, has specified these. So we don't get to like modify them. We just have to, like our job right now is just to find the optimal plan to get from A to B. Okay, good. Yeah, other questions? Okay, so, all right. So as I said, we're going to start by initializing the estimated cost to come for each vertex. So for the starting vertex, we know that the cost to get there is 0. For all the other vertices, we're just going to initialize C of x to be infinite. And then we're going to initialize the Q to have a single vertex, which is the starting vertex A. So far, it's basically the same as BFS or DFS with this additional kind of information that we're keeping track of, which is the estimated cost to come for each vertex. Okay, so we take out the starting vertex from the Q, and we start looking at its neighbors. So it has three neighbors. So it has V1, V2, and V3 as its neighbors. And as we look at each neighbor, we're going to update the cost to come for each vertex. So let's look at V1. So V1, the new estimated cost to come is 0 plus 1, right? So 0 because the cost to come for A was 0, and then 1 because that's the cost of traversing the edge that goes from A to V1. And 1 is obviously less than infinite, so we have found a better way, or yeah, we found one way to get to V1. So we lowered the estimated cost from infinite to 1 for the vertex V1. And then we add V1 to the Q. And now we're going to do the same thing for the two other neighbors of A. So let's look at V2. So we do the same kind of computation here. So the cost to come to V2 is the cost to come to A, which was 0, plus the cost associated with this edge that connects A to V2. So that cost is 7. So 7 is less than infinite, so we update that cost to come to 7. Same thing for V3, and yeah, sorry, you also add V2 to the cube. Yeah, same thing for V3, so 0 plus 2 is 2, so we update the cost to come for V3 and then add that to the cube. So that's basically the first kind of iteration of the algorithm. So at the end of that, we have some updated cost to come for some of the vertices, so V1, V2, and V3, and then we have a queue which contains those 3 vertices. So I guess any questions on that first iteration of the algorithm? All right. So yeah, let's keep going. So the interesting step in the algorithm, as I mentioned before, is what to prioritize to bring out of the queue. So what should we explore next in the algorithm? And the way Dijkstra's algorithm does this is by choosing the vertex in the queue that has the smallest cost to come estimate. So in the queue, we have 3 vertices. They have cost estimates 1, 7, and 2. So the lowest one is V1. So that's the one that we're going to prioritize. That's the one we're going to take out of the queue and explore its neighbors. And yeah, I'm going to just mark with a check mark anything that is like a dead vertex, anything whose neighbors we've finished kind of updating the cost estimates for. Okay. So yeah, let's look at V1 next. That's the thing that we prioritize. It has 2 neighbors. So A, which is already dead, so we don't need to worry about that. The other vertex is V2, which is not yet dead, like we haven't taken it out of the queue. So we're going to update the estimated cost to come for V2. So that update is 1 plus 3. So 1 because the estimate for V1 was 1, plus 3, which is the cost of the edge from V1 to V2. And we see that 4 is smaller than our previous best estimate. So 4 is smaller than 7, so we update. So 7 was the path that goes from A to V2. 4 is from A to V1 to V2. Okay, so we mark that as fully explored as a dead vertex with a check mark. So at the end of this step, we now have 2 vertices that are in the queue, V2 and V3. Okay, again, we go through the queue and find the vertex that has the smallest estimated cost to come. So V2 has a cost of 4, a cost to come of 4. V3 has an estimated cost to come of 2. So the vertex that we're going to take out is the vertex V3. Okay, So yeah, I guess let's go through the same process again. So V3 has 3 neighbors. So A, which is already fully explored, already kind of like dead, so we don't need to worry about that. V2, which is not yet dead, and B. Yeah, both of those are, I guess, alive. So V2, what is the estimated cost to come when we're looking at like how to get to V2 from V3? So it's 2 plus 5, right? So V2 had an estimated cost to come of 2 plus this cost of 5, which is the cost of going from V3 to V2. Okay, so I guess maybe just to check your understanding. So what's the update that we need to do to the estimated cost to come for V2? Any thoughts? Go ahead.
There should be no update.
Good. Yeah, no update, right? So this way of getting to V2, so this kind of new way, which goes from A to V3 to V2, is worse than our than the best previous way. So the best previous way had a cost to come estimate of 4. This way has a cost to come estimate of 7. Yeah, so we don't need to make any updates to the cost to come estimate for V2. Okay, so the other neighbor of V3 is B. So we do update its cost to come estimate. So 2 plus 7, which is 9, which is less than infinity. So we update that cost to come. All right, so at the end of this process, we have 2 vertices that are in the queue, V2 and B. Again, we take out the vertex that has the smallest estimated cost to come, which is the vertex V2, which has an estimated cost to come of 4. All right, so we mark V3 with a check mark. We explore the neighbors of V2, which are still alive. So the only neighbor of V2 which is still alive is the vertex B. So we update its cost to come estimate, 4 plus 1, which is 5, which is less than 9, which was our best previous estimate for B. Yeah, and we mark V2 with a check mark, so that vertex is also dead now. Yeah, I guess the last step is simple. We only have one vertex to take out from the queue. We take that vertex out, that's the goal vertex, and that's the end of the algorithm. Right, so we found, well, okay, so we haven't yet found or at least I haven't explicitly described how to find a path from A to B, but we did find the optimal cost of getting from A to B. So the optimal cost is equal to 5. Yeah, I guess does anyone see how to get the actual optimal path out as well? Go ahead.
You store the parent for the optimal.
Yeah, exactly. So it's the same process as what we saw with BFS and DFS. So each time you make an update to the estimated cost to come, you keep track of the parent vertex. The one thing you have to be slightly careful of is when there's no update. So we saw one step where there was no update to the estimated cost to come. There you shouldn't update the parent, right? So the parent should always correspond to the best, the parent corresponding to the best estimated cost to come. That's the only kind of slight thing you need to be careful of when you're implementing Dijkstra. That's slightly different from BFS and DFS. All right, I guess any questions on the algorithm? Hopefully the steps are clear, but I'm happy to go through anything that was not clear. Question?
Yeah, sorry. When you were at A and then when you went to V1,
Yes.
then there were 3 in the queue. So after V1, usually you're supposed to look at the neighbors, right?
Yes.
And then the neighbor for V1, the only one left was V2. So how did we skip to V3 after V1?
Let me see.
I think it's like 15.
15. Okay.
14, 15.
Okay. Yeah. So here. Yeah, marked A as a dead vertex. So we have these three vertices in the queue, V1, V2, V3. And then we're going to take out the vertex that has the smallest estimated cost to come, which was 1 corresponding to V1. And then we explore its neighbors. So it has only 2 neighbors, so V2 and A. A is already fully explored, like is the dead vertex. So we don't need to do anything with the vertex A. So the only kind of alive vertex is V2. And so we update the estimated cost to come for V2 to be 1 plus 3, which is less than 7. And then we mark that as a dead vertex. And then I guess what's the question on the next step?
Yeah.
Okay, yeah, on the next step, so we have 2 things in the queue, V2 and V3. So we take out from the queue the vertex that has the smallest estimated cost to come. So this is the main difference between Dijkstra's algorithm and BFS and DFS. So BFS and DFS, it was just kind of first in, first out, or last in, first out. Here we're prioritizing things to explore next that have the lowest estimated cost to come. So over here, between these 2 vertices, V2 has an estimated cost to come of, V2 has an estimated cost to come of 4. V3 has an estimated cost to come of 2. So we're going to take out, from the queue, we're going to take out V3. So that's what we did in the next iteration. Okay, good.
Thank you.
Yep. Yeah, other questions on the algorithm or the example? All right. Okay, so yeah, I guess let's, we went through a simple graph search problem here. Of course, what we're really interested in our motion planning algorithm, so we start off with some continuous planning kind of domain. We have some obstacles. We discretize our space, as we mentioned in the previous lecture. We get a graph, and then we want to find some optimal way to get from the red kind of star, that's our starting location, to the green star. And this video is showing how Dijkstra's algorithm explores the space. I think the cost here is just distance. So each vertex has a cost of 1, I believe. And you're also allowed to go diagonally here, I think. And I believe that the shading here of the colors like corresponds to the cost. So anything that's red has low cost, I think. Anything that is green has a higher cost to come. Okay, so yeah, it's kind of doing something reasonable. At the end, it finds what looks like an optimal path. But it's still a little bit slow, right? So it's not super efficient, and we'll talk about that. So yeah, this is the optimal path that's found at the very end. Questions?
Yeah, so with the algorithm like this, so if you put this on a real on a physical system,
Yeah.
does that system have to sort of explore the space first?
Okay, so this exploration process, you can think of as happening kind of in the head of the algorithm, head of the robot. So this is not physical exploration. So the robot is not actually moving during this process. What we're assuming is that someone has already done some kind of exploration and given you a map of the environment. And so this entire process is just happening before the robot moves. So it plans out a path from the starting to the goal location, and then the actual motion is going to be just the execution of the optimal plan that it found. You can modify these algorithms to do exploration as well. So if you don't know the mass of the environment, you can kind of like physically explore using DFS or DFS. So yeah, the robot like actually moves in different like ways, and then eventually I guess gets to some kind of goal. So that's that version of the problem is not the one we're thinking about. Here we're just saying someone has given you a map of the environment, you know the starting and goal locations. So in the planning phase, like before the robot moves, you go through this algorithm. Does that make sense? Okay, good. All right, other questions on this? Okay. So yeah, I guess just I want to really like emphasize this. So these are not like completely like intellectual like exercises, right? These algorithms like really get used in practice. So graph search is a core component of lots of different things, not just in robotics, but domains kind of beyond robotics. So if you think about Google Maps, that's a graph search problem, right? You want to get from some location A to some location B, minimizing some cost. So the cost could correspond to various things like fuel, time, distance, and so on. Yeah, I guess Google Maps has, I think it uses time mostly, right, as the cost. But nowadays, I guess they give you some like friendly like paths as well. But yeah, I think that the default is some kind of notion of something that just corresponds to time. Yeah, so Google Maps and other kind of mapping or other such like services use algorithms that are similar to Dijkstra. They have modifications, and we'll discuss some of the modifications here today. But if you're interested, there's an article that talks about how these algorithms get used in practice. All right, so just looking at this kind of exploration again. So I mentioned it's not super satisfying. Like it's exploring things in a kind of relatively uniform way. And at the end of the exploration process, it's basically explored everything like it could have explored. So there's some vertices that are like around here that you save exploring. So you don't have to explore, but everything else like over here, the algorithm ends up exploring. Which seems a bit wasteful, right? Like we know that the goal is there, so just like get there, right? Like that's what you want to tell the algorithm. But somehow Dijkstra's algorithm is not doing that exploration in a clever enough way. Yeah, I guess looking at this animation, it's kind of frustrating. So one question we could ask is, can we somehow further reduce the number of vertices that we explore during this graph search process? So that's where the A-star algorithm comes in. So this is one of the most kind of popular algorithms for discrete motion planning in robotics. So the A-star algorithm has essentially an identical structure to Dijkstra's algorithm. The only modification is going to be how we prioritize things to take out of the queue. So the queue.getVertex function is going to be implemented just slightly differently from what we did with Dijkstra's algorithm. And the specific kind of modification we're going to make for Dijkstra's algorithm, we use C of x, so the estimated cost to come to x from A. That's what we used to prioritize vertices to explore. With the A-star algorithm, we're going to use a slightly different quantity, which we're going to denote by f, which is going to be C of x plus an additional term, which we're going to call h of x. So I guess h just stands for heuristic. C of x is has the same meaning as what it did with Dijkstra's algorithm, so it's the estimated cost to come from A to x. H of x is the estimated cost to go from x to the goal vertex B. Right, so in a sense, f is kind of an estimate of the total cost to get from A to B while passing through x. Like that's the intuition maybe you can keep in your mind. So the first part, the C of x part, is the estimated cost to go from A to x. The h part is the estimated cost to go from x to the goal vertex B. One really important kind of note is that h of x, so the estimated cost to go, needs to be an underestimate, so a lower bound on the optimal cost to go from x to to the goal location B. Yeah, this is super important. So without this, the algorithm, the Dijkstra algorithm, is not guaranteed to work correctly, in the sense that it can output something that is not the optimal path from A to B. It just outputs something that is suboptimal. So you can construct examples. I won't go through this here, but you can construct examples where if h of x is not an underestimate of the optimal cost to go from x to b, then A star kind of does the wrong thing and gives you a suboptimal path. Yeah, just something important to keep in mind. So I guess any thoughts on how, maybe for a concrete motion planning problem in a robotic setting, how would we go about choosing h? So let's say we look at the problem we looked at on the previous, I guess, slide. So just a 2D motion planning problem with a starting location and a goal location and some obstacles. How would you define or compute what this h of x is for any given vertex x? That obeys, I guess, this condition that it needs to be a lower bound. Go ahead.
I start at 0.
Okay, yeah, so 0 is perfectly valid, right? So 0 is always going to be a lower bound. That reduces to Dijkstra's algorithm, right? So if you set h of x equals 0 for all x, then f of x is exactly equal to c of x for all x. And that's the same as Dijkstra. So yeah, I guess this is one way to see that the A star algorithm, that Dijkstra's algorithm is a special case of A star, like if you just set h to be 0. So you're not going to get anything kind of beyond Dijkstra if you make that choice, even though that's a perfectly valid choice. I guess any other thoughts on how? Go ahead.
We know at the very least we have to get from A to B. We also know that there's a constraint that we can't skip space.
Yep.
So you can just say that at the very least we have to travel that distance.
Yes.
And the distances are.
Yeah, good. Yeah, so you could basically ignore the obstacles, right? And you could say, if there were no obstacles, how can I get from x to b? So you could just look at, so depending on exactly what the cost is, if the cost is like distance, you could just look at the Euclidean distance. So just ignoring all the obstacles, like if I just went from x to b, what's the cost I would incur? So yeah, that's one way to get h of x, which is a valid kind of like lower bound of the optimal cost to go from x to b. So yeah, often we can get like a heuristic, get an underestimate of the optimal cost to go like relatively easily, especially for motion planning algorithms that have some kind of underlying geometric structure. Just ignore the obstacles. Then it's almost like trivial planning problem. Just compute the cost to go from x to b for that problem where you ignore the obstacles. That's an underestimate. Yeah, I guess questions on that. Hopefully that's clear. Yeah, go ahead.
So if there happens to be no obstacles in the path that you chose, does that mean that it's no longer an underestimate?
Okay, yeah, sorry. So by underestimate, really I mean less than or equal to. So not a strict inequality. Equal to is also fine. Yeah, thanks for that. Good, other questions? Okay, so yeah, I guess we discussed this already. So Dijkstra's algorithm is a special case of A star, like this set h of x equal to 0 for all x. Here's the algorithm kind of spelled out in its entirety. Yeah, part of the reason I did this is you have to implement the A star algorithm in the assignment that goes out tomorrow. So I think you can use this as a reference. But we've actually discussed all of this. So maybe I'll just go through it relatively quickly. So the first block of code here is just initializing different things. So Q, that's our main data structure. We initialize it with the starting vertex. The other stuff that's getting initialized here is the cost to come and the cost to go, so C and H. And then this function F, which is the summation of C and H. And this is the main kind of loop that explores through different vertices in the graph. So if we take out something that is in the goal, then we return. Over here, we're taking things out of the queue. The main kind of difference between A star and Dijkstra is the thing that we take out of the queue is not the vertex that has the smallest estimated cost to come, but rather the smallest f, which is the smallest the cost to come plus the cost to go, right? So that's the main modification there. So we take something out of the queue based on that f for x. We look at its neighbors, and then we do the updates for the estimated cost to come plus the estimated cost to go for the neighbors. If we find a path that's better than what we had found before, we update the estimated cost to come, the estimated cost to go, and we update the neighbors, the parent as well, which allows us to find the actual path from A to B. Yeah, so it's the exact same structure as Dijkstra. The only modification is how we take things out of the key, or what we take out of the key. Yeah, I guess questions on A star? Yeah, I mentioned this already, so you keep track of the parents, and that allows you to get the actual path. So let's look at A star. So I mentioned that Dijkstra has this kind of unsatisfying behavior of just uniformly exploring things. A star has a much more kind of intuitively appealing way of exploring the space. So it's biasing things towards the goal. So things that are closer to the goal, it's prioritizing to explore next. So you can see that a bunch of vertices over here along the kind of edges of the space are not explored by A star. So it's much more efficient in terms of the vertices that it needs to explore.
I'm wondering, is the heuristic is the only constraint that it's an underestimate? Because I'm wondering, I'm thinking of a situation where if h isn't monotonically increasing with distance, you could have one side of that. You can define h to be 0 and have a search there first before the other side and encounter the goal before.
So the only condition for A star to return an optimal plan is that h needs to be an underestimate of h star, the optimal cost to go. If h is something, so I guess what you're saying is that if h doesn't have a monotonic relationship with h star, or whatever the optimal cost to go
I
is.
can imagine just making it go to the left first just by defining h routes.
So it might go that way, but the algorithm won't terminate even if it goes one way. So it'll still explore, I guess, other ways before it terminates. So yeah, A star is always guaranteed to return the optimal path. So the optimal path may not be unique, but it'll return some optimal path. So there might be multiple paths that have the same cost. So it'll give you one of those paths that corresponds to the optimal way to get from A to B. Yeah, I think what you're saying is that, in the case that you're saying, it might be less efficient in terms of the search, but it will never terminate incorrectly. Yeah, maybe you could try to work through the example you said, and you'll see that it's still going to explore enough such that the path that it outputs is actually the optimal path, or an optimal path. Good. Okay, so let's look at Dijkstra and A star kind of side by side. So A star, so right at the beginning, A star just goes directly towards the goal. And then it hits the obstacle, and then it starts kind of backtracking and exploring things that are more and more to the side. Dijkstra has this kind of uniform exploration, and right here, A star completes the search, it finds an optimal path. Dijkstra is still going, I guess, for a while. All right, so let me just pause this for a second. So by taking into account an estimated cost to go, we're making the search much more efficient than it was with Dijkstra algorithm. I think it's kind of interesting to think about some of the history of A star. So the A star algorithm was invented back in the 1970s, so 1972, by researchers working on this robot that they call Shakey. And yeah, this paper on Shakey, which I think was published around 1972, is actually a really amazing paper. So if you're interested in, I guess robotics in general, I would recommend taking a look at the paper. A lot of the ideas in that paper are still like open, or a lot of the questions they were thinking about in that paper are still like open kind of research questions, and a lot of the ideas are still around today in state-of-the-art approaches. So I'm going to play a video of Shakey. So this was created by the inventors of Shakey. I think it's kind of amazingly modern in a way, even though the video is going to look, I guess, anything but modern.
We are experimenting with a mobile robot. We call him Shakey.
Is it audible, by the way, at the back?
Our goal is to give Shakey some of the abilities associated with intelligence, abilities like planning and learning. Even though the tasks we give Shakey seem quite simple, the programs needed to plan and coordinate his activities are complex. The main purpose of our research is to learn how to design these programs so that robots can be employed in a variety of tasks, ranging from space exploration to industrial automation. Shakey operates in this experimental environment of rooms, doorways, and simple objects. The top lens belongs to Shakey's television camera. He uses it to obtain visual information about his own location or about other objects. These walls were made high enough so that Shakey cannot see over them with his television camera. Shakey uses these feelers, or cat whiskers, to tell him if he has bumped into anything. He can push objects with his push bar. The programs controlling Shakey reside in a large PDP-10 computer and occupy over 300,000 36-bit words of storage.
That's like almost no storage by like
Shakey communicates with the computer over a radio link. We use a teletype to give instructions to the computer programs that control Shakey. Shakey reports back to us using the teletype and the cathode ray tube display. An executive program handles communication between the experimenter and the robot system. Shakey's movements are directly controlled by a set of low-level action programs. These programs convert orders such as roll 2.1 feet into appropriate commands to circuits on vehicles that control Shakey's motor. Two other examples of low-level action are pan and tilt. The low-level actions provide some of the building blocks for more complicated powerful programs called intermediate level coordinates.
Yes, I guess this is showing the robot actually operating.
Each of Shakey's intermediate level actions is designed to try again if the first attempt fails.
Yeah, so I guess the performance is not super visually impressive, but I think if you look at the paper, like you'll appreciate that there's so many ideas that they came up with, including A star. And a lot of the problems that I mentioned that they were thinking about back then are still relevant today. So there's some computer vision, so the robot actually had a camera, which it was using to figure out where obstacles were in the environment. The obstacles were kind of relatively uniformly colored to make the computer vision problem a bit easier. It was using some planning algorithms like A star. It was exploring the space. So it actually didn't assume that it knew exactly where the obstacles were beforehand. So it's actually exploring the space like physically, like incrementally. That version of the problem we'll talk about later on in the course. But yeah, if you're interested in this, I posted a link to the video, and as I mentioned, check out the paper as well. Okay, so yeah, I talked about A star back in the 1970s. So what's happened since then in planning? So as with many other fields, like subdomains of robotics and other fields in general, machine learning has had a massive impact on the way we do things. So one kind of direct way that you could think of incorporating learning into planning is by learning the heuristic. Right, so in the example with the star that we discussed before, we were kind of manually specifying what the heuristic should be, like it's some underestimate that we come up with, like Euclidean distance from a vertex to the goal vertex or some other kind of valid under approximation. But one thing you could do is just learn what that heuristic, like what that cost to go like estimate is. And the way you could do this is by solving lots and lots of motion planning problems. So we have a bunch of different graphs, a bunch of different planning problems. You could solve each one of them, and then you could fit some function like a neural network that gives you an estimate of the cost to go from some, like any vertex x to the goal vertex. And that's actually what, well, that idea is what was used in the AlphaGo system that beat the world champion in Go, back in 2016. So they were using some graph search algorithms. So the specific algorithms they use is what's known as Monte Carlo tree search. But the main idea was to basically estimate the cost to go, like estimate like the value function as it's known in the learning kind of domain for different like configurations of the Go board. So if you have a particular configuration of the board at some given time, what you want to do is like just figure out what's the next best move, and you could do a search to find a move that's going to lead to kind of the maximal like probability of success in the future. That search potentially is, or not potentially, I guess it is like interactable. Like there's lots and lots of different possible sequences that you need to explore. So to truncate how much you need to search, they were basically using a learned heuristic. So yeah, the way kind of it maps to our like setting is instead of using a manually specified h of x, you learn what that h of x from lots of previously solved planning problems. We're going to say much more about machine learning later on in the course, but this is kind of just giving you a preview of how it applies to motion planning. Questions on any of this? Okay. All right. So yeah, we're still some time. So the last thing I want to discuss, so I want to just like zoom out a little bit and talk about some broader implications of some of the technical materials that we've discussed so far, and specifically the broader implications of this notion of optimality. So I think someone asked, like, how does the cost function get defined? Is it just user defined? Like, how do we come up with it? So that's the question I want to consider at the end of this lecture. So far, yeah, as I mentioned, we've encountered this like notion of optimality twice. So when we looked at feedback control, we said we want stability and optimality. LQR gave us a particular kind of notion of optimality, like the quadratic costs on state and control inputs. And then we looked at optimal planning algorithms as well in today's lecture. So we consider relatively simple like cost functions. With LQR, it was just the quadratic like penalties on the deviation in state and deviation in control input. With like these planning algorithms, we were basically saying the cost could be like time or distance or energy or something like that. But it turns out choosing a good cost function for a more kind of challenging task is a pretty like challenging problem like by itself. So the main challenge is how can we ensure that the cost function that we define, so this is some mathematical object, a mathematical function that we're defining, that's a really kind of precise thing, somehow captures the less precise thing that we have in our head, right, that we want our robot to do. So how can we take a task and specify it in terms of a cost function? So this problem has a name, so it's called the value alignment problem. So the problem of specifying via a kind of precise function what we want our robot to do, how to make sure that it aligns with our values, right? What we as humans want our robots to do. So to make this more concrete, there's a famous kind of philosophical thought experiment. So this was introduced by the philosopher Nick Bostrom around 20 years ago now. So it's called the Paperclip maximizer. So almost like any discussion you hear about the value line problem makes a reference to this Paperclip maximizer thought experiment. So the thought experiment here is really simple. So you basically have a AI system or a robot, in our case, whose only goal is to make as many paper clips as possible, right? So it's a really simple cost function. So here you can think of it as a reward function. So the robot gets a reward of 1, let's say, for every paper clip that it manages to produce. If you're thinking about it as a cost, you can think of a cost of -1 for every paper clip that it produces. So we're minimizing the cost, maximizing reward. So yeah, the robot starts up making some paper clips, makes more and more paper clips, and keeps making more and more paper clips. So that's all it does. All right, so I guess what's the problem? So here's what Nick Bostrom, who came up with this example, said. So the AI will realize quickly that it would be much better if there were no humans, because humans might decide to switch it off. Because if humans do so, there would be fewer paper clips. Also, human bodies contain a lot of atoms that could be made into paper clips. So the future that the AI would be trying to gear towards would be one in which there were a lot of paper clips, but no humans, right? Yeah, I guess what do people think of this? Is this reasonable, or is this useful? This thought experiment of the paperclip maximizer. Any objections, or do you think this is actually what's gonna happen? Go ahead.
Didn't it realize that it needed to go to the asteroid belt to mine paper, whatever material you're gonna use to make the paper clips?
Yeah.
To eliminate humans. I feel like there are many possible outcomes to something like this.
So there are many possible avenues, but I guess it's trying to find the optimal, solution, which is to maximize the amount of paper clips. So I guess what you're saying is it could do something else first, maybe it goes to the asteroid belt, mines some materials, makes paper clips, but then it's going to realize, oh, there's more materials here on Earth, which is humans, so I'm going to turn humans into paper clips as well. The other kind of interesting comment here is the point about switching the robot off. So the sentence where it says, so the robot would quickly realize that it would be much better if there were no humans because humans might decide to switch it off. So the technical term for that is an instrumental goal. So the robot was never instructed to try to not be switched off. But if its only goal is to maximize paper clips, so it cannot do that if it's switched off. So as an instrumental goal, as kind of a side effect, it's going to try to prevent itself from being switched off. And yeah, I guess humans might switch it off, and so it's going to try to eliminate humans according to this thought experiment. Good.
This sounds familiar. I'm not sure what it is, but there's something somebody's laws. There's
like Asimov's laws?
Yeah.
Okay, yeah, sure. Yeah.
Is this at all tied into that?
Yeah, it's kind of tied into that. So Asimov's laws are, well, I guess they're kind of fictional, and yeah, I mean they come up a fair bit when we think about philosophy in robotics. But yeah, Asimov's laws are kind of hypothetical laws that you might want to encode into a robot, so like not harming like humans. So here we're saying that we're not encoding like any kinds of laws, like Asimov's laws, into our robot. We're just saying maximize paperclips, and these are some of the side effects that might then like entail. So one potential solution to this is to bake in like rules for our robot to prevent this kind of thing from happening. But that actually turns out to be like fairly challenging by itself. So I guess Asimov's like books, like the reason they're interesting is because the laws are not like kind of completely like watertight. So his like stories basically involve like exceptions like to the laws. So if the laws were like completely watertight, I guess there would be no books that that he wrote that were interesting. But yeah, it's like hard to kind of manually specify like what these laws should be. But that's one possibility. Go ahead.
So like I guess would you want to like instill like morals into the AI or something that aren't like hard set laws, but just
Yeah.
like, sort of general? Like,
Yeah, definitely. So that's what we would like. So we'd like to encode values, I guess. So that's where the name like value alignment problem comes from. So if we could somehow encode values into our robots, we could maybe prevent something like this from happening. But yeah, it turns out to be relatively challenging to do that. I guess other thoughts on this? Like, does anyone think it's not realistic or not worth thinking about? Go ahead.
I mean, it doesn't really seem quite applicable to the technology that we're developing, at least for now.
Yeah.
Because we're designing systems in such a constrained
Yep.
space. It doesn't really, like something like this wouldn't actually be.
Yeah, and I think that's a kind of reasonable like counter argument. Like if you look at our robots today, I showed like videos of many bloopers in lecture 1. We're like pretty far from like this level of like capability. But I guess the proponents of this kind of thinking say, okay, like maybe we don't have to worry about it now, but like maybe we'll see like some pretty rapid like progress as we have in the last like decade with machine learning in particular. So we need to think about this to be prepared for like the time when like we are actually close to this kind of capability. And it's interesting to think about. Did you have a?
Yeah, I guess, I mean, doesn't a learning algorithm optimize some cognitive or optimize value over like a set of parameters?
Yeah.
And, like, if one of the parameters that we decide to bake into the algorithm is not like the existence of humans,
Yeah.
then it's just not going to consider that as
Yeah.
something, right? Like,
Yeah, you could like bake in like some kind of additional like values into the robot, but then you have to think about like all the possibilities. Like here, I guess he's just laying out some potential like side effects of just maximizing paperclips, but it might be like hard to enumerate like all the things that could go wrong. So another kind of neat example of this is if you ask a robot to, if you give a robot like rewards for cleaning things up in your like room, let's say, so maybe this is a home robot who gets a reward every time it like cleans something up. The robot could decide to like break things in order to clean things up, right? So it like breaks things, cleans it up, and like gets a reward. So that's another neat example. Go ahead.
I think this is interesting in the sense that like you kind of have to think how could this be used incorrectly. So like I know when it's like my background is medical devices,
Yeah.
so when you're designing things that people will use, one of your assumptions is that everyone is going to try to use it wrong at some point. So you kind of have to like build safeguards into it, and so that kind of is what this makes me think of.
Yep.
If you're encoding something for a robot to do, like think like your logic might not line up exactly with like
Yep.
how you laid it out.
Yeah, exactly. Yeah, I guess other thoughts on this? Okay, so yeah, two possible, okay, maybe, sorry, before that. So yeah, just to be concrete, so this value alignment problem is like how can we make sure that our cost function, like this mathematical object, like actually aligns with our like human values, and we need to somehow take into account side effects, so the robot like breaking things to clean them up, or the robot eliminating like humans, or instrumental goals, which is like trying to prevent itself from being switched off when we specify some cost function. So there might be, yeah, some possible objections or like counter arguments to this like paperclip maximization kind of thought experiment. One, which I think some of you like mentioned, is that it sounds somewhat like far-fetched. Like we're pretty far away from like robots having like enough capabilities to really need to worry about this. And the other one is like, can we somehow, or can we not somehow just like learn values from humans? So if a robot is like observing humans kind of going about doing things, can we somehow learn from that? The second kind of bullet point here is going to tie into our like discussions on learning later on, and maybe if we have time, I'll say we can revisit this value learning problem. But I just want to address the first one. So like maybe we're not at the level of capability where it makes sense to really worry about this, but I think we actually are. So we don't see this yet in the context of robotics, but we do see it when we're thinking about like social media, like platforms in particular. So yeah, I guess I would argue, lots of people argue that this value alignment problem is already a real like problem that we're encountering today when we think about like social media, like algorithms that like prioritize what to show you on a social media like platform. So these algorithms have some objective. So they're not like pure like engagement, right? I guess the like usual like stick that people beat like social media like companies with is, oh, like you're just trying to maximize engagement. If you listen to like interviews of like heads of these companies, they say that it's not like purely engagement. They're trying to maximize like other things, but there's some kind of baked in objective, like some like cost function or reward function that the algorithm is using to prioritize like what to show you and what to like popularize and like maximizing, and they have like some correlation with engagement, right? So I guess if they had like no correlation with engagement, then these companies would not necessarily make a profit. But whatever like the actual like objective is that they're maximizing can have like pretty like adverse consequences, as I guess we've seen over the last few years. So I think even though in robotics we're not at the level of capability where like the value alignment problem is necessarily like a really like pressing challenge, we see this in other domains. So it's kind of interesting and important, I think, to think about. All right. Yeah, I guess any last comments or thoughts? Okay, I think that's all I had. So I'll see you on Thursday.